Hello and welcome back to Everyday Physics. This video we're going to be continuing to look at the question, how does a street lamp work? In this video we're going to look at the photoelectric effect and how this can be used to tell a street lamp when to turn on. Okay, in this video we're going to be looking at the photoelectric effect. The photoelectric effect is very exciting because it was one of the first solid pieces of evidence for quantum mechanics. So to understand the problem with the photoelectric effect, we first need to understand a bit about electromagnetic radiation. At the beginning of the 20th century, it was understood that light comprised of waves, and these waves could travel through space, through a vacuum. The wavelengths of the waves gave light with different colours. So for example, light with a wavelength of 690 nanometers looks red. Light with a wavelength of 400 nanometers looks blue. Blue light has a bit more energy than the red light. We can go down to the UV range, the ultraviolet range, which is shorter wavelengths than blue light, and then on to X-rays. At the other end of the spectrum, we've got infrared light, which has a longer wavelength than red light, and then we go up to radio waves, which have wavelengths of up to kilometers. So this was well understood at the beginning of the 20th century, and we knew that these light rays could travel through space at the speed of light. Okay, so the speed of light is 3.00 times 10 to the 8 meters per second, and that's how fast light travels in a vacuum. If it gets into water or another medium, it slows down a little bit, but through a vacuum, the speed of light is 3 times 10 to the 8 meters per second. So the problem was that we couldn't use this understanding of light to describe some of the phenomena that people were starting to observe. In 1887, Heinrich Hertz observed the photoelectric effect. He observed that when you shone light onto a metal, electrons were released. It was J.J. Thomson who discovered that the released particles were actually the electrons. But then it was observed that there were actually some problems with our understanding of light and what was actually observed. It was observed with some metals that if you shone red light onto the metal, no matter how intense the light got or how long you shone it for, no electrons were released. But if you shone a higher frequency light, like with a shorter wavelength, like blue light or UV light onto the metal, then you did get electrons released. Now this makes no sense if we take the classical picture of light as made up of waves, because waves carry energy, and so with the red light falling on the metal, it should be giving the metal more and more energy as we leave the light on there for longer and longer periods of time, and so eventually there should be enough energy in that piece of metal so that the electrons can jump off the positive nuclei of the atoms because they have enough energy. But this wasn't observed. So what was happening? It was Einstein who came up with the explanation of what was happening. And this was the basis of quantum mechanics. So in 1921, Einstein got his Nobel Prize for services to theoretical physics, and especially for his discovery of the law of the photoelectric effect. So Einstein actually never got a Nobel Prize for special relativity or general relativity, which he's most widely known for. He actually got his Nobel Prize for quantum mechanics. So how did Einstein explain this photoelectric effect? Well, he said maybe instead of considering light as a wave which travels through space, carrying energy, we could consider light as a particle. So light is made up of little particles called photons. When we shine light on a metal, we're pushing lots of little photons at that metal. So what Einstein said was that we were shining little particles, photons, at the metal. Those photons had to have enough energy to allow the electron to escape. If the photon didn't have enough energy to allow the electron to escape, then over time the atom that it hit just returned to its normal state and that energy was lost, but not in the form of an electron with kinetic energy. If, on the other hand, the photon did have enough energy to cause an electron to escape, then the atom would absorb that photon, the electron would get excited, and the electron would move away from that piece of metal with some energy in what's called the form kinetic energy, which is just the energy of movement that we'll be looking at later. And so there was a very special point there. There was where if you have a higher energy than some critical energy, the photons have enough energy to cause the electrons to escape. If the photons have less than a certain energy, then there isn't enough energy for the electrons to escape. So let's look at some of the formulas involved in this. So Einstein said that the amount of energy a photon had was given by E equals hf, where h is equal to 6.626 times 10 to the minus 34 joule seconds, and f is the frequency of that photon. So the frequency is related to the wavelength. We've got a formula there. The speed of light, or the speed of the wave, is equal to f times lambda. So if we know the wavelength, we can get the frequency using that formula. Okay, so we've got the photon. It's got an energy E equals hf coming in to hit the piece of metal. Now, to cause the electron to escape, it has to give that atom a certain amount of energy. That's how much energy the atom needs to allow its electron to escape from the orbital out to infinity so that it can escape from the atom. Now, this amount of energy is called the work function of the metal, and it's different for different metals because some metals hold on to their electrons more tightly than other metals. And finally, the remainder of the energy, if there's any left from that photon energy, hf, it goes into the kinetic energy of the electron which escapes from the metal. So the formula that Einstein came up with for the photoelectric effect is hf is equal to the work function, which is often written as phi, or sometimes it's given the letter w, plus the kinetic energy of the electron, of the photoelectron. Okay, so this explains why when you have red light, which has a much longer wavelength, a much lower frequency, it doesn't have enough energy to cause these photoelectrons to escape. If you have shorter wavelength, higher frequency light, such as blue light, then the photons do have enough energy and they can escape. So we get electrons escaping from that metal. Now, we make use of this in our streetlights because we have a detector there. It's like a piece of metal. When there's light shining on it during the day, it's producing these electrons that can be made to move along like a current. So we can produce these electrons and we can actually measure these electrons. Now, when the sun goes down, there's not that light hitting the street lamp anymore or our photodetector, and so we no longer have these photoelectrons produced. And the photodetector senses that there's no longer any photoelectrons, and so it tells the street light to turn on. Let's do an example now. What is the maximum kinetic energy an electron can have if blue light with a wavelength of 475 nanometers releases it from cesium? Cesium has a work function of 2.1 electron volts, and this is equal to 3.36 times 10 to the minus 19 joules. So to get from electron volts to joules, you just need to multiply by the charge on an electron, which is 1.602 times 10 to the minus 19. So we know that the photon energy, hf, goes into the work function, so releasing the electron from the atom, and then any remaining energy goes into the kinetic energy. So we've got our maximum kinetic energy there. So in this question, we haven't been told what the frequency is, we've only been told what the wavelength is. So we'll need to use our equation, c is equal to f lambda, where c is the speed of light, to relate the frequency and the wavelength. So we will need to rearrange this to find f. So we have that f is equal to c, the speed of light, over lambda, the wavelength. So the speed of light is given by 3.00 times 10 to the 8 meters per second, and the wavelength is 475 nanometers. So this is times 10 to the minus 9 meters. So we enter these numbers into the calculator, and when we do that, you should get 6.32 times 10 to the 14, and then the unit for frequency is the hertz, so that's hertz. Or if you want, you can put inverse seconds as the units. So now what we need to do is we need to substitute our frequency back into this equation here. So now we're going to substitute down into this equation. So h, that's Planck's constant, it's equal to 6.626 times 10 to the minus 34 times our frequency, 6.32 times 10 to the 14, and that is equal to the work function, and we use the one in joules here because this will be in units of joules. This is in joule seconds and this is in inverse seconds, so the units here are joules. So this is 3.36 times 10 to the minus 19, and then plus RKE max. And now what we need to do is solve this for the maximum kinetic energy. So we just do a bit of algebra. We can subtract this number from these multiplied together. So KE max is equal to these two multiplied together, which is 4.18 times 10 to the minus 19 minus the 3.36 times 10 to the minus 19, and solving that we get 8.25 times 10 to the minus 20 joules. Now if you wanted to give this in electron volts, which you could, you just need to divide it by the charge on an electron, 1.602 times 10 to the minus 19. If you do that, you end up with 0.51 electron volts. Okay, now let's assume that the question goes on and asks us, so now we're asked, would red light with a wavelength of 650 nanometers allow electrons to escape from cesium? Well, with the red light, we once again calculate the frequency. So frequency is equal to C on lambda, which is 3.00 times 10 to the 8 over the wavelength, which is 650 times 10 to the minus 9. We type this into the calculator and we end up with 4.62 times 10 to the 14 hertz. So now we can work out how much energy this red photon has. So we use E is equal to HF, which is equal to 6.626 times 10 to the minus 34 times the 4.62 times 10 to the 14. And we see that this is equal to 3.06 times 10 to the minus 19 joules. That's a 0. Now the work function is 3.36 times 10 to the minus 19. So this red photon here doesn't have enough energy to allow the electron to escape. So the electron cannot escape with red light. So let's have another look at how street lights can make use of this. Okay, so the intensity of the light hitting the photodetector is related to the number of photons hitting it. So sometimes, if it's a very cloudy day during a thunderstorm or something like that, the intensity of the light hitting the photodetector drops a lot, and that can cause the street lights to go on during the day when there's a big storm on. The number of photoelectrons produced is proportional to that intensity of light, as long as the light has enough energy to cause the photoelectrons to be produced. So by detecting how much photocurrent we get, we can determine when to turn the streetlights on and when to turn them off. What I have here is a solar lamp. This solar lamp works off similar technology to the street lights for detecting whether the light is on. On top of the solar light, we've got a solar panel. When light falls on the solar panel, we get electrons generated through a similar effect to the photoelectric effect, and these create a current which charges up a battery there. When the light turns off, the photons stop falling on the solar panel, the electrons stop being produced, and so there's no current, and so the light now knows that it's time to turn on. So in a street lamp, this will happen at dusk, or if it's a very cloudy day and the intensity of light falling on the photodetector panel drops off. Special thanks to Jonty Horner for filming this, and also special thanks to these people who provided images that we made use of during the video.